Okay, now we're going to look at discharging a charged capacitor. So imagine that you've built a circuit to charge up your capacitor, and then you remove the battery so that you're not accumulating any new charges, but you have a charged up capacitor. So you got positives here, negatives here. It's fully charged up. You remove the battery, but you close the circuit with a resistor. Well, you have a closed circuit, and you have now a reason for the charges to move. So you're going to get current flow off of this capacitor, and it's going to run through the resistor for a while. The difference is we don't have a battery replacing the charges. So eventually these charges are going to run out. And that probably gives you an idea already of what the graphs should look like if the charge is eventually going to run out. But what I'd like to do is go ahead and let's do the calculus to show the in-between. What does the curve look like for the charge and the voltage on the capacitor and the resistor? Okay, so here we have capacitance C. It's starting out with a charge of Q max, and we have a resistor here R. So current is going to come out this way. It's going to come out of the positive side. So if it moves through the resistor in this direction, we have high energy side, low energy side, and then for the capacitor, plus side and minus side. And just like we did for the charging capacitor, let's do one loop. Let's do one loop. So the voltage on the capacitor, if I'm going clockwise, this is a gain from minus to plus. So voltage on the capacitor, which would be Q over C. And then the voltage drop on the resistor, because when I go clockwise, I'm going from high side to low side. It's a drop of IR. And you're going to notice here then that Q over C is equal to IR. And that's pretty simple, but I want to write this as a differential equation, so I need to find the hidden derivative. This one is a little bit more challenging, okay? In order to relate current to charge on the capacitor, the current is due to charge leaving the capacitor, not charge being accumulated by the capacitor. It is only getting current because charge is leaving the capacitor. So in order to relate Q and I, Q and the current, we need to say that the current in the system is minus dq dt. It is, again, the charge is leaving the system. So current is due to charge leaving the capacitor. Sorry, this should be I. The current is charge leaving the system, minus dq dt. Okay? So then I can write this loop rule as Q over C is equal to minus dq dt times R. And I'm going to go ahead and move minus R to the other side to get the derivative by itself. So we get minus Q over RC is equal to dq dt. Multiply both sides by dt. I get minus Q over RC dt is equal to dq. So the first rule is satisfied, but of course the second rule is not satisfied in that my variable q needs to be over here with the small factor dq. So I get minus 1 over RC dt is equal to 1 over q dq. And now I'm ready to integrate. So let's put the integration symbol there, and let's also figure out the boundary conditions. Well, at t equals 0, when you are starting out here, you are starting out with a fully charged capacitor. So this fully charged capacitor starts with a charge of Q max, and then sometime later, we want to know what that charge is. So we'll say here, Q is a function of time. Sometime later, what is the charge? Don't forget here, it's starting out charged up with a charge of Q max, not 0. Okay? So these integrals are actually not too bad. This minus 1 over RC is a constant, so this becomes minus T over RC. Integral of 1 over Q is just the natural log of Q. So we get natural log of Q. But we want to evaluate it from Q max to Q as a function of time. Okay? So minus T over RC is equal to the natural log of Q over Q as a function of time minus the natural log of Q max. Okay? So of course, when we subtract natural logs, it's the same thing as the natural log of the quotient. So minus T over RC is equal to the natural log of Q as a function of time divided by Q max. And we want to get rid of the natural log, so we're going to eify both sides. So e raised to the power, so we get e to the minus t over rc. Notice you get that tau, time constant, again. You get this e to the minus t over rc that we saw in the charging capacitor is equal to q as a function of time times q max. And this is a pretty simple algebra. I'm just going to multiply by q max. E to the minus t over rc is equal to charge as a function of time. So what we see for the discharging capacitor is that it's an exponential decay. It starts at some charge q, and it's going to decay to 0. So we're losing the charges without replacing them. We can move on from here, and we can find the different voltages. For example, voltages and currents as well. Let's do voltage on the capacitor first. So voltage on the capacitor we know is Q times C. So here we get Q max times C, e to the minus t over RC. So QC we know is just, I'm sorry, voltage is, so let's go ahead and find the voltage on the capacitor as a function of time. We know voltage is just Q over C. So if I take the time dependent charge divided by the capacitance, that would be Q max over C, e to the minus t over RC. And that is, well, what is Q max over C? That is the initial voltage, right? So we'll say this is V initial e to the minus t over RC, which if we charged it up with a battery, that would be V of whatever battery you charged it up with. But I'm just going to leave it as V initial, whatever voltage it started out with. We could also do current as a function of time. Current as a function of time we know is going to be dq dt. And that is derivative of Q max e to the minus, we said current is minus dq dt, my apologies, because it's the charge is coming off of the capacitor. So minus dq dt. Well, charge as a function of time was Q max e to the minus t over RC. The derivative of that is e to the minus t over RC times the derivative of the exponent. So we get minus Q max e to the minus t over RC times the derivative of the exponents. That's minus 1 over RC. Minus and minus makes a positive. We get a current as a function of time is equal to Q max over RC e to the minus t over RC. But we know that Q max over C is just V naught. So we got V naught over R e to the minus t over RC, which I'm going to call I max, or you could even call it I naught. It was the initial current times e to the minus t over RC. Okay, and again, it's another exponential decay. It looks like for the discharging system, we get a bunch of exponential decays. The last one would be the voltage on the resistor. Voltage on the resistor is a function of time. We know would just be current as a function of time times R, right? V is equal to IR. So let's take our I max times R times e to the minus t over RC. So I'm just multiplying this guy by resistance. But what is I max times R? When the voltage is a maximum on the resistor, that would just be our V initial. So V initial e to the minus t over RC. What's interesting is that is exactly equal to the voltage on the capacitor. We said it was V naught e to the minus t over RC. But if you look at our circuit, you've only got two elements. And these two elements would have to have the same voltage. If you took a voltmeter and you placed it here and here, your leads, take the voltage reading on the resistor would be identical to the voltage reading on the capacitor, because nothing interesting happens between those two leads and the capacitor or the resistor. So those voltage readings would have to be identical. So for the discharging capacitor, it's pretty simple. You know the four graphs are all exponential decays. Charge as a function of time is an exponential decay, and it starts out with whatever charge you had placed on the capacitor. Voltage on the capacitor is an exponential decay. It's also starting out at some value V naught. Current as a function of time is an exponential decay. It's starting out as V naught over R. And then the last one is voltage on the resistor. also an exponential decay, but it starts out also with V naught. So it looks identical to the capacitor graph because the voltages have to be the same. So that one's probably a little bit more simple. I would expect that if an RC circuit shows up on the exam, you're probably going to have to do both charging and discharging. So keep that in mind. Make sure you can go through both of the problems and send me any questions that you have. Try to do some free response that you see in the workbook.